I'll do a quick dive into union find, make a small tweak to it, and then look for some fun groups to play with for it, and then see if we can use it to try and reduce some pressure on the propagator network again, which seems to be a recurring theme for me. What is union find? How many people are comfortable with like disjoint sets or disjoint or union find? This has come up for them before.
Can you give me the one sentence?
I want to be able to create sets, union sets, and ask if two items are in the same set.
Okay.
These are the only operations you're allowed. Turns out you can implement this in n inverse Ackermann n time. So inverse Ackermann basically means it's going to be like 4. For any amount of work that you could do in this universe. Sure. So it's, you know, log of log. It's ridiculous. It used to be log. It used to be like log star, and then they put the bound to n, alpha n, which is the inverse Ackermann function. Nice. So n alpha n time for n finds and n union, or n finds plus unions in my problem. Okay. And there's various ways to hit this bound. I'll talk a bit about the sort of standard way first, and then I might throw a reference to a slightly better way. I don't think we have time. I'm going to skip that.
Sorry, I can miss. What is alpha?
Alpha is inverse Ackermann. It's you take, you know, the two arguments, feed them not to feed it. Find me an Ackermann value that is larger than whatever n I have. You know, it doesn't take many iterations through Ackermann to get pretty big. Like I said, read this as a basically constant. Like, and I hate people who I hate it when people say something is effectively constant. This is as close to effectively constant as you can get. Okay. It's like the slowest growing function that we actually use in computer science. So I have this ability to union. Now the typical implementation strategy is something like this. I create sets by creating a node that sort of points to itself. And then I union them by pointing, like climbing to the root of what, let's say I have a node down here, and I'm going to union it by pointing it to another node. And then I will point the root of one of my sets at one of the others, at the root of the other, to merge sets. So that's all we're doing. Like we union by pointing one node probably at the root of the other just because it'll shorten the path length. And then we have some options to try and improve our set here.
So is it the category of sets we're dealing with here, or is
No. Like literally, I have a make set as an operation that makes a thing, and I have the ability to ask, and I have a union operation that takes two sets and modifies them to be the same, to glue together by mutably changing this pointer. So like if I were to union these two sets, what I would do is do that. And then this is rather inefficient because to compute the root of this set, which is how I use to check if two things are in the same set, I have to follow a chain of pointers. Yeah. So there's a couple of strategies. One is called path halving and one is just called path compression. Path halving is I move everybody to their grandpa. Like I just like skip a level. Path compression involves forwarding everybody all the way to the root. Like I walk through this thing, find the root, and as I walk back down, I just point everybody that I found to the root.
So is the root a smaller set than the other one, or is it?
Nope. This whole thing is one set. If there's a chain of things to you,
okay,
you know you are and you are the top of the thing.
Okay.
This whole thing is one set. Okay. The idea is you're given a node, you walk up until you've found the thing that points to itself. I'm given another node, walk up until I found the thing that points to itself. Yeah. Compare these two things for pointer equality. That tells me whether or not these are in the same set. Okay. So if I want to just test whether or not these two members belong to the same set, ask if they have the same root.
Sure. That makes sense.
Okay, that is the basic design of Tarjan-style disjoint sets. It's one of the things that made Tarjan famous back in the day. he did like 50 of them. Especially this bound. Okay, and in order to get this bound, we need two components. One is you need to use either path compression or path halving. And the other one is you need to do something called union by rank or union by size. So it turns out when I'm picking which one of these I should link into the other, if one of these has lots and lots of children, there are more paths that would be made long by linking this one into this one than if I were to link this one into this one. Right? If you think about it, if I were to extend this way, there's going to be lots of paths that were made one longer. If I link this one into this one, there are fewer paths that are made one longer. So I should bias in favor of the one that makes fewer paths long, because the longer paths mean more path compression has to happen later.
So then you need to know how many pointers there are into yourself in order to do that?
Yes, so the root node should maybe hold like the number of children. So this would be union by size, which is sufficient to do this thing. So path compression and union by size is a simple way to do this. The slightly nicer or more efficient if you have a lot of children thing is to do something called union by rank. And what you do is you start with the rank 0, and when I always union like the thing with the lower rank into the larger rank, and if we ever have two things of the same rank, I pick one arbitrarily, and I increase the rank of the new root. And that is sufficient to obtain the exact same characteristic, but the ranks grow slower than counts. Because they only grow when I merge two things of the same rank. So I do less writing to the rank number.
Is that a Galois connection?
I don't know. I don't think it is.
Good.
So this is disjoint sets, or disjoint set forests, or union find, however you want to call it.
Okay.
This is sort of a workhorse of unification as well, because typically what we'll do is our unification variables will have this flavor. I'll take a chain of unification variables and they'll just like identify a common root for them rather than have a term pointing to a term pointing to a term pointing to a term. Like if you have a term that points to just a variable term, well, let's try and short circuit this and do the same sort of rank system in order to make unification, like built on mutable pointers, go a little bit faster. Okay, a lot faster.
So when you're passing elements of these sets around, they're basically just pointers to these nodes?
Yes. So I'm going to hold on to a reference to this sort of thing. And one of the things we talked about in the first session briefly was the fact that I use real references and modify my notion of non-determinism a little bit to allow me to actually use real pointers. So, so I get to use real pointers in my programming with I'm using non-determinism. The trick to make this interesting and make it relevant to the group stuff is that I could decorate these edges with some group that I want to have act on the target. So I can say, like, instead of saying x equals y, which is what we're basically saying by unioning sets, I'm making assertions about x is y, and then we just union find, we find the root to check to see if like this is true or whatever, and then we union to smash them together. I want to be able to say like x is y plus a constant. So now x and y are variables representing integers, and now I have integer shifts. This is a group. I can glue together my constants. So x equals y plus a constant, y equals z plus a constant.
So constant is the delta?
It's the delta that I'm now going to be gluing together. So if I ever glue two edges together that have different constants on them, I just do the group action, not do the group action, just use the group merge on the elements. The fact that it's a group means that if I need to say x and y, if I need to link one way, I use the element. If I need the other way, I need the inverse. If I ever need to go, x is y plus a constant, but y is z, or z is y plus a different constant, this does the right thing. You accumulate the group for the path of the root, you accumulate the group for the path of the root, and smash the elements together to figure out the distance from x to z.
Right. So you can maintain this low strength merging by flipping the group.
So this works for basically any group that I might want to have act on my elements of my union find structure.
Cool.
So I use a lot of interesting groups here. In particular, we've looked at this plus C example. But another example that I find particularly valuable, that I was very pleased to find, and I don't know that I've seen so much in literature, or seen it all in literature really, is I'm going to say like y equals ax plus b. So I have an affine transformation of x. But a and b are integers now. And if I want this to be a group, I have to be very careful, because we can subtract b from both sides, and we get y minus b equals ax. But now to go all the way to get x in this form, I need a to have an inverse. So if I'm working with the rationals or the reals or something like that, this just works. But if I'm working with the integers, I can't just take any integer and look for an inverse that is an integer. There's only 2 of them that have inverses that are integers. So in a ring, there's something called a unit of the ring, which is an element of the ring that has a multiplicative inverse. So when you say you have a ring rather than a field, you don't always have division. You can sometimes have division. And like the complex numbers, if you're 1 unit away from the origin, if you were, I guess you'd have to be like Gaussian. So you'd have. Like,
there are 2.
Huh? Why are there 2 for the integers? We have 1. 1 has a multiplicative inverse that's an integer.
What's the other one?
What's minus 1? What's minus 1 times minus 1? Now that's 1 as well. So we have a multiplicative inverse for minus 1. We have a multiplicative inverse for 1.
Okay.
So why do I care about this? Like, we've been talking a little bit about at various points, like x is in the element as the range 1 to 5, and y is in the range 1 to 5. And then I start saying things like x is less than y, and I use this to propagate and lose this member and lose this member. But now I want to be able to say, well, y is z. Or something like that. Y is z plus a constant. Or minus z plus a constant. So I want to say like x is minus y, and instead of using a propagator to push the upper bound of x to become the lower bound of y, and the lower bound of x to become the upper bound of y, what I want to do is use unification to reduce the pressure on the propagator network. And again, we said before that if I had no propagators out of a value, then I could avoid trying to ground it. So the unification mechanism doesn't require me to ground the term. So what I'm basically saying is I can take z as an interval that's exactly the same size as y, and it's entirely determined by the value. Every member of z is entirely determined by the member of y, and vice versa. So these are in 1-to-1. These are 2 intervals that are of the same size in 1-to-1 correspondence. You know, like one is like an inversion of the other, or possibly straight, shifted, and possibly inverted. So this particular group is something that I'm using a great deal of in Guanxi. Because it lets me talk about something like, hey, x is the absolute value of y. Now I can split on the positives and the negatives, and then, so that's one bit of non-determinism, because we're in this overall monad that's non-deterministic.
Sure.
And then take the positive cases and unify it in this way, directly with y, and then take the negative cases and unify it directly with the negation of y. And now absolute value just became one little non-deterministic choice and unification, and the propagator's gone. Otherwise, I was going to have to do all this laborious work to try these 2 things together, and absolute value would stick around, keeping me propagating, and possibly introducing non-termination. So it was going to be too strict. Did that make sense? All right. So this notion of taking a group action and modifying unification with it is, I think, is particularly pleasant. We talked about SAT solving. I have a library called ersats, which is a binding to external SAT solvers. One of the things I can do is I could improve that, because you can look for, find me the equations that basically asserts that x is y or x is not y. You use the 2-element group, call them identity and not. The inverse of not is not. And then describe its action on a literal. And then I can unify chains of like if x is y and y is not z, and z is not w or whatever, I can chain these things together and talk about them all being one variable, which reduces the number of variables I send to my SAT problem. So this is just using the 2-element group to shrink problems that I'm going to feed to a set solver, which is relevant to all this stuff because I'm trying to tie all this stuff to S&T solvers and sat solvers and stuff anyways. We can turn around and view this as a 2-element group with an action on the integers where the action is negation. And then we can, if we care about semi-direct products, this group here is actually the semi-direct product of this 2-element group and this.
So do you still express this in the same like set membership node diagram? Like these sorts of logic?
Yeah, well these things like internally, I have like this chain of things to the root interval.
Yeah.
And then what I'm going to wind up with is a sort of set of propagators that are like listening to the lower bound or the upper bound of the interval. And now I have a problem. I have propagators that were listening to someone over here that's at a different position than propagators that were listening to this interval. When I union these two intervals together, I need to move all the propagators from here up to the root. So if I narrow the interval that's associated with the root, I will narrow those intervals. But now, these things are expecting updates to an interval that's in a completely different position than the interval that I'm actually changing. So what I need to do is I need to be able to relocate. Ah man, this is just like we just talked about this. I need to be able to relocate this interval, or all of these propagators, so that they hear the messages at the position that they were expecting. And I need to be able to do that in one time, hopefully. So I can union these sets of propagators into a big long catenable list of propagators that is now listening at the new location. But I have to give you the sort of group action. I need to give act on this with the group to push the propagators so they hear the message at the right position. So that should be O1 to act and O1 to append, as long as I have a catenable list that was O1. And did I give the Okazaki tricks to actually get the list append down to O1? I think we didn't. We ran out of time.
No, that's fine.
So I'll deep dive into that real quick, and then we'll just go into like code browsing mode for the last of our scheduled time. Okay. So I think I made a relative or something. Shit, where did that code go? Action. So down in here, we were working with lists. To get list append down to O1, we need to turn to Chris Okasaki's purely functional data structures, and in there he builds a bunch of things like queues that have O1 SNOC and O1 unconst. So a queue for him looks something like this. I have a queue, and it's made out of like a simple one would have two lists. And this one's maintained in reverse order, and then whenever this one runs out of elements, I reverse this list and I put it over here. So I'm only ever going to consume this once this list is sufficient. And he's got versions of it where you maintain counts and you carefully balance these things to keep these counts roughly balanced and do all this stuff. The one I actually use is based on a thing that uses a third list, that forcing the next element in this list is actually forcing me to do one step of the reverse to reverse this element into this list. It's in Chris's book. It's not informative for me to walk through the construction. I have code in Coda.
Sure.
The idea that you can use this queue data structure to build a queue that has O1, SNOC, and unconst is what matters. Okay? But what is it made out of? Lists. If only I had some way to make lists able to be relocated in O1 time. So what I could do is I can bolt a delta into my queue, and I can take all of Chris Okasaki's work, and I can steal it, and I can make a queue that can be relocated in O1 time. Good. This is a building block. Now that I have the queue, I can build a catenable list out of queues, because Chris has a whole thing for doing this. A catenable list, a bootstrapped catenable list, is either empty, or it's a const of an A onto a queue of catenable lists, where each of these catenable lists is known to be non-empty. If they're not non-empty, then this just makes the one of the operations that I do not O1. It's O1 plus the number of non-empty lists in this thing.
Sorry, what does the catenable list get you above the queue itself?
Having a catenable list gives me O1 append. So now I have, basically, you give me two catenable lists, and I can glue them together in O1 time. So this gets me O1 snock, O1 unconst, O1 const, O1 append, O1 rel.
Yeah.
And basically everything you want to do except index into this thing is O1.
How good is indexing?
Indexing is, you'd have to do it linearly, or you would have to modify the queue or something like that to keep counts. Tell me whether I should work in the head or tail. I mean, I don't have a good bound. I don't have a bound for indexing. It's not an operation I try to support here. So think of this as, if you're working with a finger tree, appends would be logarithmic in the size of the smaller of the two. Here, appends became O1 in exchange for losing indexing. We just think of this, don't use this when you need indexing, and you're good. But this data structure's, I mean, it's better than a list. You can basically say, whenever I was going to reach for a difference list, maybe I should reach for something like this, if we talk about like the kind of thing that we talked about after the session last time. This is a workhorse for me. This notion of a cat-nibble list with some kind of group action baked into it. So I use this for like cat-nibble lists of tokens where the tokens are relocatable. Like let's say my Lexer spits out one of these sort of things. Now I can glue together the tokens that came out of separate lecture passes over different lines or something like that. I have versions of this for Dyke languages, for recognizing languages of parentheses and brackets and braces and stuff like that in parallel. In this case, I'm using it to maintain the list of propagators that are like listening for changes in the root interval, and in such a way that I can relocate the list of propagators to be listening at the, to hear the message of the new location at where they were. And to see something like source, domain, internal. This code is awful. I'm going to do a simple theory of equality using union find first. So I have a term has a unique ID and a reference to content, and content is either we are a child of another term, or we are the root, in which case I have a rank, and I have, in my case, I have a list of known disjoint terms. So we're going to do union find, but now with also the ability to assert that we're disjoint. So you can tell me is and isn't. So you can create new terms, assert that this term is another term, assert that something isn't another term, and then ask me to decide whether or not two terms are equal. Yes?
So the S is the ref type, right?
Yes.
Okay.
So S is like a region parameter like STS. And down here what I'm doing is something like internally I have this find and find X combinator that I use to implement is and isn't. And is and isn't are the operations you're allowed to say given two terms. I will like just assert that they're equal or assert that they're not equal, and this will blow up the universe if you ever like make me make a chain of things that's impossible to satisfy. Like X is Y, but Y isn't Z, and Z is X, then I'll just blow up the universe because you've made me say something impossible. And what I'm going to do is at the end, when you ask me in language, in the EDSL for Guanxi, if M is N, I'm going to say, well, if I try to assert that M is N positively, if I try to union them, does it work? If so, true. If I try and assert them negatively, if they're already in the same set, then I blow up the universe. Otherwise, I get back false, and it'll give back both answers in a way that has made the assertion about the world in that case.
What does open angle bracket dollar do?
This guy.
That's it.
This is
Const fmap.
yeah, it's like fmap const this thing.
Okay.
Replace the answer of this with this, because these things were returning units,
Okay.
and I want true in this case and false in that
So
case.
this is saying if I can't prove that they are equal, maybe I can prove that they aren't equal?
Now this is try it both ways. Make the assertion that they are equal. And it either blows up the universe or I successfully return true. Make the assertion that they aren't equal. So this like asks the question, is it consistent that they are equal? Is it consistent that they're not equal? So you could get both answers.
Or both of them.
Or one or both of them could blow up.
Yeah. Okay.
So this is sort of the way, like an example of the kind of thing that you would do in a sort of logic programming-ish setting, where now I have a very simple theory of equality.
Okay.
Once you start dealing with terms where like this is a very simple theory of equality where I don't have terms that contain other terms. If I need that, then the like refutation list of like things that I'm definitely not equal to becomes more complicated. I need to know like all terms that can contain my term. There's a some terms of art in this space that aren't terribly informative to that. But I just wanted to offer up a very simple theory of equality as an example of using the union-find structure.
Yeah.
And like I said, it's a slightly modified union-find structure because at the root I have this hash set of other roots that I'm known to not be equal to. So when I assert something, so find here will take a term, climb to the root, tell me the rank for the root that I actually found, tell me the set of hash sets that are in it, and give me the pointer to that root. Like this is the pointer to the content, which is definitely a root, where this was the rank and this was the hash set. I had to touch them anyways, so I might as well give them back. That's what so this is sort of giving me the pointer that points to this stuff, because I'm going to probably change it. And then in is, what I do is I find the root of m, I find the root of n, I assert that one of these guys is not in the other one's rejection list. If so, I blow up the universe. I compare the ranks. In the case that one's smaller than the other, I point one at the other's root. But now I have to union the set of things that they're known to be disjoint to. And there's a small modified ref thing here to insert.
So if you know that they're the same, then you know that the disjoint one from this one and the disjoint one from this one can be combined.
Yep, and then I have to go through and I have to everybody who could possibly be looking for the other one as the root of things that it's disjoint to needs to be remapped to look at the new root.
So are you adding a pointer to a new root, or are you rewriting the?
I'm rewriting the pointer to the from the old guy to the new.
So the old one kind of disappears, and then you just shuffle all the information into this new node.
Yes, and so like I've consolidated all of the things that were known disjoint to the new root.
Yep.
And I've rewritten everybody else who was like known disjoint from this guy.
Yep.
To now be known disjoint from the new root.
Okay.
And then isn't goes through and just finds the two roots, asserts that the two roots are not the same, because otherwise we've already failed.
Yep.
And then inserts into their relevant roots this negation information to make sure that it never happens in the future.
Okay.
Like this is really like imperative, messy nonsense, but it should hopefully be relatively hidden from you in the sense that the user sees is and isn't and decide.
Right. This is pretty actually.
So I offer that as a very, very simple theory of equality. And then if we look at something like the interval arithmetic domain, I have a much scarier root. My root here has its rank. It has either a batch of propagators that are waiting for me to have a first assignment to my lowest bound. There's often a bunch of things that are just waiting to wake up on the thing ceasing to be bottom, which is minus infinity. Or I have a lower bound, which is an integer. Similarly, I have things waiting for my upper bound to change, or I have an integer. And I have things that are waiting for any improvement in the lower bound, things that are waiting for any improvement in the upper bound, and things that are waiting for me to be fully grounded. Like you have to, like this propagator only fires when it's down to an actual integer. It's like if you have an integer, if you have a constraint that's something like x is not 5, this thing can check for those and blow up the universe in that case. And then we can relocate one of these roots by relocating all of the pieces in it.
Beautiful.
And then the content chain is something like this. My child points to the next thing up with one of these affine transformations. And then an interval itself is either a known integer, or it's an affine transformation applied to content. And this lets me apply an affine transformation to an interval directly without having to go through and do any pointer arithmetic.
Sorry, what's content? Oh, it's the
Content is this chain of pointers that lead to the ultimate root.
Okay, gotcha.
So I have a chain of affine transformations that are applied ultimately to some root, which is this monster.
So this is still letting you reuse the same content as different ranges by applying this group.
Yes, I can apply this affine transformation, this ax plus b thing that we talked about earlier.
Does that also end up like saving you a fair amount of memory then, as well as performance, or does it not really?
It's really the fact that it can keep me from bottoming in places that I would otherwise have to bottom.
Okay.
And what's case up in the root? Case up in the root.
Where are we looking at?
Up. Yeah.
Which one?
Last line, arc of case. So there's P's, those are propagators.
Oh, K's. So these are, let's see where I've got K's here. There's a captainable list of these propagators. In this case, this is expecting a C of M, which is the content. So it's going to be fed the content here. And the other one's going to be fed an actual integer. So the content is what is the current interval? And so this propagator will, this thing will fire with whatever the current affine transformation is, and this is the sort of root affine transformation. So when I relocate this thing, I'm going to shift this around. And I'm going to get the affine transformation I'm actually running at.
So is Z only a single?
It's just
constant?
an integer.
It's just, so is it a specific integer, or is it a shared constant that you just apply affine transformations to?
No, Z is just, literally Z is just the type integer.
Okay, cool. But you could still apply affine transformations to it if you really want.
Yes, and it's an instance of, there's a class of things that acts on, just like the relative stuff before, and Z is an instance.
So I mean, presumably though, you could just have Z equals unit representing 0 and then apply affine transformations to bump it up or bump it down. Or
so the thing here is like, I don't want to have that be, like, I'm using R low here to say, here is my actual lower bound, and a set of propagators that they're listed. I either have I have an actual lower bound,
right. So otherwise you'd
or
have
anything. I would have to use something, I would have to use integer here.
It would be worse, but
it wouldn't save me anything really.
I was just wondering if it was possible,
I think you could get away with it by and large.
Okay.
But I still need to be able to talk about how these two things are different.
Sounds good, thanks.
And then I need to pass something to tell you what the lower and upper bound are when I call you. I think you just push the problem around. So what do I use this stuff for? So here's a whole pile of ugly looking assertions that say this integer is less than this interval. That's like me clipping the interval on the lower range with an actual constant. Or asserting that this interval is equal to this integer. This is like forcing me down to an actual concrete value. And it will either succeed, in which case, knowing that this integer was in the interval, and we accept this as a refinement of the current interval, or it blows up the universe because this integer was outside the interval. This one here, we are going all the way to ground, and saying this interval is definitely not this integer. This would be an example of the kind of thing where that wait for this to hit ground and then blow up. Logic would fire. Here is when this interval is bounded below, this action should run, and it's sort of used to do that slow wake up machinery that we talked about before. Here we're listening for any improvement on the lower or upper bound. I'll get you the improvement on those bounds, and you can transfer it to whatever you want to do. So these are like actions that will happen on wake up. These are like on change kind of callbacks.
When would a propagator want to listen to a lower bound versus a higher bound?
So like if, let's say I had to brute force implement negate. I could on low produce the higher bound of an upper one, of another interval, and on high produce the lower bound of the other interval, like by negating the bound you gave me.
Oh, I see. Yeah.
Instead, negate actually does unification with the affine transformation being minus 1 plus 0, or minus x plus 0.
Yeah. Okay, yeah. So is that a difference between your logic and some other ones? Like, do some other ones do it with that?
I don't know how many people actually have this sort of thing.
Okay, cool.
It's pretty weird.
Yeah.
So this is sort of the assertion that x equals this affine transformation of y. Like directly built, like equating these references with an affine transformation along the way. This is what we were talking about. X equals y plus a constant, x equals y, some action. Here is like x is the signum of y, or y is the signum of x, sorry. and then I carefully track through all the ways that, you know, signum would work in the num class or something like that. It's the same thing. Negating an interval is applying an affine transformation to it.
Check the math. This works.
This one was fun. Negate, similarly, is just asserting that these two things are exactly equal.
So,
Absolute value tries to get out of the way by letting me either assert the positive or negative case. If we have a concrete value. Otherwise, clamp me below and then do some fiddly stuff using a combinator that I basically hide from the user, like that looks at the current value of the range to see if I could get away with giving you simpler propagators.
what's the intuition for the applicative instance of the logic here? Is it just
So we're like, the applicative is basically asserting more things to get, like we're in the monad, what we're able to do is work with references and backtrack.
Okay.
So we're in this backtracking monad that has access to IOREFs, more or less.
Okay, sounds good.
And then refinement takes an interval and maybe grounds me out. But it does it by like cutting my interval in half. If I have an interval from minus infinity to positive infinity, I'll split, say, the positives from the negatives. So I'll have the non-negatives and the negatives as two separate intervals. And then, given an interval that's, say, strictly positive, I will take its lower bound and like double its lower bound. And I'll take the finite interval from lower bound to double its lower bound and like 2n plus 1 to infinity. So that gives me a small interval and an unbounded interval. So I can take an unbounded interval and get me a finite interval and an unbounded interval. And any finite interval, I keep cutting in half.
Sure.
And the reason to do this is if I ever had like something like an x is less than y assertion, the moment the x is definitely, the whole interval of x is less than the whole interval of y, I can throw this propagator away.
Right.
And then there could be no propagators listening. And the moment there's no propagators listening, I don't have to actually finish grounding. So the goal was to avoid doing an enumeration from minus infinity to positive infinity by grounding incrementally.
Okay, so you can slowly throw away chunks of this interval, but
Throw chunks of the propagators away and then hopefully not have to ground some of my variables. Whereas concrete just repeatedly does refinement until we get down to ground. But this will bottom very easily, so we shouldn't use this very often unless we absolutely have to know all the values in my interval.
Right.
And then I can do things like, between this and this is an interval, this is sort of dot 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 combinator. So this just lets me write, you know, x is 1 dot 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 5. Or we can assert intervals that we can have, maybe we can have like minus infinities or positive infinities. This takes me out of finite domain solving, and now I may bottom out because my theory is not fully decidable. Yes?
Awesome. What was the class monad signal?
Monad signal. Monad signal basically lets me add a sort of last, when I'm done with all of, like I have references, and I have a sort of, I am done with everybody else, so I'll now finalize and run things to ground call. I can assert a thing to do at the end. That's what this grounding call is at the end. So there's an action that will be run after we've, like if I just had like finite domains implemented as sets of integers, and then what I'm going to do is I'm going to like let you narrow the set of integers that like could possibly be by propagation. We still haven't asserted, even though we've established arc consistency for each one of my individual predicates, we haven't established that my predicates together don't actually rule out other things. So that grounding step, that last step of going down to like check this one, and then push that information to the rest of the network, and then check this one, and check this one, and check this one. That is going through, looking at, in this case, my reference, seeing if anyone is listening to it. If no one is listening to it, I just sort of report, okay, the current solution has whatever multiplicity the width of this interval is. Like we multiply there's going to be n many copies of whatever solution I find as like logical copies. Like I should report like x is less than y, how many solutions are there? Or something like that. It should tell me the actual count correctly rather than just say, okay, well, like these were all indistinguishable. So it sort of just keeps track of a writer of a product, which is the in the product monoid, which is like just sort of like what is the multiplicative count of how many solutions I found. And then otherwise, if someone's actually listening, refine the interval and then go back to refining this this interval. My bottom here is the interval from infinity minus infinity to positive infinity. We can assert that two intervals are disjoint. In this case, when one gets improved, then it makes this positive assertion. The removal here needs to actually be done. This is a missing piece of code. But it's the reason for the refinement. But this is an example of it's a fairly hairy pile of code, and it should basically be encapsulated, and then you can use it. You just do the interval arithmetic inside of Guanxi, and you don't care about it. So earlier we talked a bit, I mentioned sort of loosely that there's sort of like a chain of adjunctions or something like that of different abstract domains. This is sort of the simplest abstract domain that I have. And it's already hairy.
Pretty, yeah.
So, how much time do we have?
5 minutes.
Huh? How long? 5 minutes, oh dear. All right, we're gonna do 5 minutes of very, very quick adjunctions. Because I have one thing that I really want to talk about. I may run over, and I do apologize. I'll try not to run over too long. Can we bring the lights up, or?
Yeah, there's a switch on the top one.
All right. So what I have is a series of abstract domains that I might want to do interpretation in. Like for instance, instead of working with concrete integers and then trying to logic program with those and then trying each individual leaf case, we had an example where we were just doing interval arithmetic. And then I was trying to work with intervals and then throw things away while I'm still in intervals. Okay? And the reason I cared about that is something called natural domain SMT, which is I am working with the conflict-directed clause learning thing that we had from SAT solving the first day, where we were able to say, well, I guessed this and this and this and this, and that was definitely not the case. And so let's run De Morgan's law through that statement and get a new clause that we can add to our problem. Okay? Now that my formulas are things like x is within this interval, y is within this interval, blah, 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 this is definitely not the case. I've bracketed some kind of box that I know the answer is definitely not in. What I could do is I could say, I want an interval that we're definitely outside. Well, I can't have one interval, but I have non-determinism. So I can say, well, I'm above this line, or I'm down in this thing, or I'm over in this region, or I'm down in this region, right? So I could carve my universe into disjoint regions like I would as a graphics person, like play with a BSP or something like that. Okay, or in this case, you got like a KD tree. I want to look at the negation of the interval that I was trying. And now basically what I've said is like my conjunction of statements can now be negated, at least non-deterministically. And so now I check this region, this region, this region, this region, and I will never try another thing in this region. Okay, so this is, we're doing the conflict-directed clause learning. We're learning we're not in here, so don't go there again. So this worked for intervals, but intervals are the simplest domain that I care about. They're actually the only non-relational domain that I care about. So, what are the workhorse domains that I care about? The next domain that I care about is something called octagons. Oh, I'm sorry, I have to keep going with this. Which is something, I'm gonna talk about a quick, simple one. Let's say I had something like x minus y is less than or equal to 3, and y minus z is less than 4. I can add these equations and get x minus z is less than or equal to 7. So you can view these numbers as like weights on edges from x to y and y to z, and I'm computing shortest paths. Okay? So what we're now doing is we're talking about pairs of variables and this sort of relationship between them. If I ever wind up with a path from x to x that has negative weight as the shortest path, I should blow up the universe because I've required that x is less than x. So we're doing like Bellman-Ford to push these weights around in O(n) cubed time in the number of variables I have. I can solve this. And we can modify this a little bit to allow for like equations like plus x plus y is less than or equal to a constant. And I can, you know, this could be plus or minus, this could be plus or minus. So I can allow for positive or negative weights, and this lets me do things like, instead of just dealing with intervals, now given a pair of variables x and y, I can cut extra 45-degree pieces off of it, and I'm left with some kind of octagon for any individual pair of variables. But then I have given any pair of variables, there's separate octagons, and these octagons now propagate between themselves. I realize I'm totally timed up. I'm still going to go. Anybody who wants to bail can bail. So we're doing okay here. We've got these octagons and we're now pushing information around. What I can do here is I can build sets of variables that have constraints between them. We'll use union find to glue these universes together. Okay? And now what I'm doing is within the universe, I have at the root, I have a matrix, which is this, the shortest path matrix, which then squared in size. And I use Bellman-Ford to keep refining this as I add more, as I glue the universes together. I kind of glue these matrices on sideways and then compute the paths through. Okay? So we're good. This is sort of end of the third, end of the fourth time. By the time I get done with that extra thing, if I actually want to make sure that there's integer points inside of it, I need to spend end of the fourth time. It's a little bit more costly than the Bellman-Ford thing. So we've got octagons can be propagated in end of the fourth time while we're working in this abstract domain. And there's a chain of adjunctions where we start from, like, intervals can be turned into octagons that make no 45-degree cuts. Octagons can be computed, I can take their approximating interval. Okay? So I can kind of come up and down this sort of lattice of abstractions. But now octagons couldn't model something that needs a non-45-degree cut. Let's say x is 2y, or something like that. If I have something that has like a sharper slope, what I have to start doing is approximating that with like a bounding octagon, which gets me closer than like if I had to work with the bounding box. But it's not tight, right? So I can talk about polyhedra, where I'm allowed to like take an arbitrary linear combination of variables, and I can look for points inside of these polyhedra, and I can look at their bounding octagons or bounding intervals if I want to move down the chain. But now polyhedra are like 2 to the n to maintain, and we can do Presburger arithmetic bounds, which actually turns up like Polylabs does a bunch of stuff for LLVM optimization that way. But now we're 2 to the 2 to the 2 to the n. So my complexity of my bound maintenance gets more and more ridiculous. My constraints become more and more ridiculous to maintain the higher up this lattice I go. But at Presburger, we can compute things like fixed points directly in them and all sorts of crazy things. So you get a lot of power out of this theoretically super expensive thing. And maybe it makes sense to come up to this more accurate domain, compute the thing, because what I'm going to get is some slop. Like when I move down this hierarchy, I'm going to like try some cases that definitely do not contain an answer. But the bookkeeping of maintaining this extra, more accurate thing was too high. So I have one more point, and then I'm totally going to break. And this is sort of, I think the sort of punchline that I wanted to sort of show here is one more trick that is just not in literature that I think is important for abstract interpretation for constraint programming. And the idea is you give me a one of these like graphs or hypergraphs, basically, like all of the dependencies between x and y and z. Let's say we had my x, you know, I had x is less than y, you know, y is less than z, or I've got these constraints. I have the path from x to y, the path from y to z. I can modify Bellman-Ford to tell me sort of a minimum set of edges that would generate the matrix that has the minimum cost. So get rid of this redundant edge, unless there was a path from x to z, it was actually cheaper than the path through here. So get rid of the redundant edges in your Bellman-Ford. Find me a generating set for the minimum spanning paths. Now what I can do is I can take this whole graph and I can look for a set of vertexes in the graph that if I were to cut these vertexes from the graph, I would partition my graph into two or more disjoint subsets. So the reason I care about this is if I can enumerate how many cases there are for like choices of values that I could assign, like now if I were to just like brute force assign all the values to x, y, z, like the values that I just cut, how much was it, right? That I paid some cost, some constant k, some size of set. Now I've got like I to the fourth plus j to the fourth. If this is smaller than n to the fourth, which was the original set size, I should make the cut now. I should carve my universe into smaller universes by guessing early. Now, here I'm doing it to the fourth. Finding the set, I have to consider like 2 to the n possibilities. I probably can't do it for octagons. But the moment I move to polyhedra, I'm paying 2 to the n for every step. So I should maybe, between every step, be willing to just try all of the possible ways I could cut up my matrix and then build these smaller matrices. And when I move to Presburger, I'm paying 2 to the 2 to the 2 to the n. So it's definitely worth it to me to try and carve up my world into smaller spaces. As long as like I have a small, like narrow isthmus through which my graph is connected. And I've never seen this thing in literature, and it's a trick that I really wanted to include in this. That's why I decided I was willing to bull through and go over. So there's more stuff in there. This is sort of like a greatest hits of random ideas I've had while playing with logic programming. We did not really get a chance to like turn this into a logic programming thing so much as here's a bit of algebra and stuff like that of, you know, not quite how I spent my summer vacation, but how I spent my winter. Feel free to come up to me with questions later.
Awesome.
Thank you.
Thank you.